Push and pop in stack. In the last lecture, we learned that stack is a last in first out data structure and that it has 5 primary operations. And the main point was that all the 5 primary operations in stack can be performed in order of one time and order of one space. So this is the main speciality of stack. In this lecture, we are going to take two of those primary operations, that is push and pop, and we are going to see how these are actually implemented so that those operations can be done in order of one time. So this is what we are going to discuss: the array implementation of push and pop, and then the linked list implementation of push and pop, because we already discussed in the last lecture that both push as well as pop can be implemented using arrays as well as linked list, and in both these implementations we should be able to do in order of one time. So how do you actually achieve this? How do you implement this? This is what we are going to learn. Let us take array implementation first and let us learn about push. Okay, so before going to push and pop, let us have an introduction of how array implementation is done. Let us say this is your array. You have an array here. These are the elements in the array. So let us say the size of this array is 6. So totally you can have 6 elements in this array. So the stack elements, you're going to implement a stack. So the elements of the stack, they will be stored in this array. And the top of the stack, you always should know which is the top of the stack. For that, you will have a top pointer or an index. This will be used to track the position of the last added element, that is the top element. So when I say pointer, in array context, instead of a actual pointer, you are going to have a variable called top. So in this variable, you will be storing the index of the top element. So here let us say it is index 0, 1, 2, 3, 4 and 5. These are the indices of those positions. Now, if you want to have some element, you will insert into this array and you will always keep track of what is the top element here. So how do you start? You initially keep top as 0. So 0 is the top, which means the array is empty. So top will always be pointing to the next available position in the array, right? So 0, if top is 0, that means it is an empty stack because the next available position is index 0, which means there are no elements in the stack at all. So let us see how push is implemented. Push. In order to implement push, you place the element that is to be pushed at the top index. This is the first step. So before this, because this is an array, you have to be careful that you should not exceed the length of the array. Okay, we'll discuss that after we discuss push. So in order to push, you have to place the element at the top index. So for now, 0 is the top index. Let us say I want to push an element 28. So I'll push 28 here. So as soon as I insert an element, I should increment top by 1. So top will become 1. So from top 0, it came to 1. So this is my top now. So what does my top point to? Top point to the next available space. If I want to push, let's say one more element, I want to push for 41. So I'll push 41 here because presently top is 41. Then I'll increment top to 2, which means top is now pointing to this one. So this is how you generally push an element onto stack. What is the time complexity? Time complexity is order of 1. It is constant because you just have to insert at the top position and increment top by 1. You don't have to traverse through anything. And what is the space complexity? For this particular push operation, you are not taking any extra space. You are just inserting in the already existing array. So space complexity is order of 1. One thing that I told you, you should be careful about is that because this is an array, it has a maximum size. For example, in this array, maximum size is 6. So whenever you get a push operation, you should always be careful whether the array has already exceeded the maximum limit. So what happens if, let us say you already had elements in all these and your top is now pointing to this, that is top is 6. What if top is 6? Top is already pointing out of the array. So you can't insert anything more into this array. So whenever you want to do the push operation, always keep a check at first whether top has already exceeded the array size. If it has exceeded the array size, you should abandon this push operation. If it has not, you can do push as we mentioned. That is, just see wherever is the top pointer. Let us say till this it is filled. See wherever is the top pointer. Insert the new element there. Let us say 30 is your new element. And then you can increment the top pointer. This is how push is implemented using arrays. Let us see the next operation, which is pop. How is pop operation implemented? In order to implement pop, you just have to do the reverse of what we did for push. So before you pop, always see whether the array is empty. Because if it is already empty, you can't pop. Let us say 0, 1, 2. This should be 2, 3, 4 and 5. These are the indices. And let us say my top is already 0. That is, there is nothing to be popped off. In this case, top will be pointing here. What happens if I decrement top from here? Top will go out of array index. So, whenever you get a pop operation, you should first check whether the top is already 0. If the top is already pointing to 0, you should abandon the pop operation because the stack is already empty. Okay. The next thing is, how do you implement pop? Let us say there are some elements here, 11, 20, 15, 7, 99, 71. Okay, these are the elements in this array. Or let us say one is free, up to 99 it is filled. So where will my top point to? Top will point to the last cell. So my top will now be 5. This is the situation. In this case, if I want to pop, the first step is to decrement the top pointer. So the top pointer I am going to decrement to the previous one. Now it is pointing to 4. So my top will point to 4. Once I decrement top, the next step is to return the element that is at the top pointer. So at my top pointer, presently the element is 99. So I know 99 is the element on top. I'll return 99 in the pop operation. So whichever is on top of the array, I got it. But if I want to pop again, what will I do? I'll decrement this pointer again. It will come here. Now the element is 7. So I'll pop 7. If I'm asked to pop again, I'll again decrement it. Now it is 15. I'll take 15 out. So I told you, wherever your top pointer is, that is the next available slot. So if I want to, let's say, push now. I want to push 13. How will I push? The top pointer is here. So I'll push 13 here and then increment the top pointer. That means the stack is now having 3 elements. So wherever your top is pointing to, that will tell you what is the size of the stack. Okay. So what is the time and space complexity here? It's a constant operation. You are simply popping or pushing. You are moving one step ahead or behind. So time is order of 1. Space is also order of 1 because for popping you are not going to anyway consume any space. So one thing you have to be careful with this array implementation is that the stack's capacity, your stack's capacity, it is limited by the size of array. Because here your array is having a total size of 6, which means your stack can have maximum size of 6. So whatever be the size of your array, that will always limit the stack size. And in case, let us say you want to resize the array, you want to increase the size. In that case, resizing will take order of n. So that is not feasible. Why does resizing an array take order of n? Because let us say I already have an array of size 6. I want to increase the size of this array. We already discussed in array lectures that array is always stored in contiguous memory locations. In memory, each array element should be stored in contiguous locations 1, 2, 3, 4, 5, 6, so on. So it should be next locations. You can't have half of the elements here and half of the elements somewhere else. That is not possible. For linked list, that's okay, but not for the array. So because you already allotted space for array, some other maybe some other data structures, other processes would have occupied the space here and on the other side, that is near to the allocated space. All the space would most probably be occupied by some other process. In that case, if you want to resize this array, you don't have space to expand. So what you will have to do, you will have to copy all these array elements in order to a different memory location. And after that, you will have to provide extra space there. This is why resizing an array will take order of n time. Because of that, while you are implementing stack using an array, you have this limitation that the stack size will always be limited by the size of array. So in order to overcome this, what can you do? I told you stack size is limited by size of array, which is a limitation, and you want to overcome this. For that, the solution is linked list, because linked list is dynamic. So you no more have any restriction on size. So how do you implement push and pop using linked list? That is the next question. So in linked list, as you already know, each node will contain data and a pointer. Pointer means pointer to the next node. This is how a linked list will be implemented. And there will be a head pointer which will always point to the first node in the linked list. Let us see how push and pop are implemented. I want to implement, let us say, push. Okay, I want to implement push. In order to implement push, the first thing is I want to create a new node. Let us say these node values are 60, 57 and 33. Let my new node's value be, let us say, 59. This is my new node. So I want to insert this into the stack. That is what is called as push operation. So always the top of stack, you should know the top of stack and you should know which is your stack. So we already said that each node will have the data and a pointer which will point to the next node. And we always have to maintain the head pointer. And the speciality here is this head pointer will serve as the top of the stack. In array, we saw that we had to maintain a top pointer separately. In linked list, the head pointer of the linked list, this will also serve as the top of the stack. So here you know the top is presently 60. So stack is like this, okay? 33 is the element on bottom, 57 is the next element, 60 is on top. So that is how stack is in a linked list. Wherever your head is, that is the top position. I want to insert 59. Where do I insert 59 in the stack? I should insert on top. Instead of 60, 59 should be the top now. So how do I make it? This is same as insertion at the beginning in a linked list. We already learned how to insert a new element at the beginning of the linked list. So the same is what you have to do. This element, it was 59, right? So I'll have 59, let us say. This node, first I'll make it point to the present head. So present head is 60. I'll make 59 point to present head. This is the first step. And the second step is to change the head, that is the present head, to point to new node. So present head will now point to 59. Head will now point to 59. If you see now, 59 is the top element, 60 is the second element, 57 third, and so on. So this is how push is done in linked list. What is the time complexity? Time complexity is order of 1. We already learned that inserting at the beginning of a linked list will take order of 1 time. The same operation is what you are using to implement stack. And space complexity is again order of 1 because you are not using any extra space other than the node that you need to insert. So that is a constant time operation. So it is order of 1. So this is it about push in a stack using linked list. The same situation, let us say stack is implemented using linked list and I want to do pop instead of push. So how will I do pop operation? Let us say so here unlike the linked list, you don't have the option of deleting any element. You can only pop from the top of the list. That is the rule in stacks. So how do you pop? In order to pop, it's very simple. You just have to first retrieve the value. Presently, whatever is pointed by the head, you retrieve the value 59. Once you retrieve the value, you can change the head to point to next element, that is 60. Whatever was the head, make your head point to the next element. Now this element 59, this is not reachable at all. You can free this off from the memory using free operation. So in the previous lectures also we discussed that this free operation has to be done if you don't have automatic garbage collector in your language. If it is there, it will automatically do. So there should be some way by which memory is freed. Okay. So this is how pop operation is implemented. What is the time complexity? It is order of 1 constant because you are simply changing a pointer to point to the next. And space is again order of 1 because you are not using any space here. If I want to pop 60, what will I do? I will again increment this head pointer to point to 57. Now 60 is not reachable. I can free this off. So this is the pop operation. The next question is how to make this decision of when to use arrays and when to use linked list in order to implement stack. So this is the thumb rule. Whenever you want to decrease memory usage, but you know what is the maximum size of stack possible. In that case, you can use arrays, because in arrays, you don't have to use memory for pointers. You only need memory for the element. So that is the positive part of array. On the negative side, array size will always limit your stack size, because of which, if you know the maximum size of the stack that you need beforehand, then you can choose array implementation. If you don't know the maximum size, if you have to dynamically change the size, then you always use linked list. But the disadvantage with linked list is, linked list, for each element you have to store extra memory is required in order to store the pointer, because every node will come along with a pointer to the next node. In order to store this pointer, you will need extra space.